There we go. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, so rule 3, and get right into it here, said what? It says that if f and g are holomorphic at z0 and g has simple 0 at z0, then the residue of f of z over g of z at z0 is just equal to f of z0 over g prime of z0. All right. So here's the proof. It's in 2 stages. If f has a 0 of order n greater than or equal to 1, then, of course, we can write f of z is equal to z minus z0 to the n times h of z, where h of z is, of course, holomorphic at z0, and h of z0 is not equal to 0. Also, g of z is equal to z minus z0, right, times, let's say, h sub g of z. I'll put this h sub f up here so we can keep them straight. H sub g of z, where hg of z0 is not equal to 0, and hg of z is holomorphic at z0. Thus, what? So then, let's put the pieces together. Hence, if we look at f of z over g of z, what do we got? We have z minus z0 to the n times h sub f of z divided by z minus z0 times h sub g of z, right? Which is equal to z minus z0 to the n minus 1 times h sub f over h sub g of z, right? And let's see here. So we're assuming that n is greater than or equal to 1, right? So what's that say about f of z over g of z? Yeah, f over g of z0 is just equal to what? 0. Because if we plug it in, we get 0 times something which is non-zero, which gives us 0. And what's that show? If n is equal to 1, Oh yeah, my proof has 2 cases. Fair enough. So this is for n greater than 1. Now let's look at Sam's. If n equals to 1, then what? Then we just have not 0 necessarily, but we have what? F of z naught over g of z naught equals to what? HF of z naught over hg of z naught, right? Which is not equal to 0. But in either case, what can we say? In either case, n greater than or equal to 1 gives z naught non-singular, right? Because we can just plug in the point, or, I mean, okay, fine. Technically speaking, what should I do here? To be fussy, and I should be fussy here, then what? I should be looking at the limit as z goes to z naught of this, right? And that is what we get hf of z naught over hg of z naught, because the z minus z naught terms cancel, right? Fine. So anyway, it's either the quotient is continuous, right, with a 0 at z naught, or in the case n equals 1, it's actually a removable singularity, right? Anyway, in both cases, the Laurent expansion centered about z naught has 0 residue, right? So in both cases, the residue at z naught is equal to 0. So but what can you say about the formula, f of z naught over g prime of z naught in both of these cases? See, if you check it out, this is also going to be equal to f of z naught over g prime of z naught in both of these cases. Why is that? Well, if n is greater than, first of all, g prime of z naught is non-zero because it's a simple 0, right? So there's no division by 0 there. Second of all, if n is greater than 1, then f of z naught is 0, right? Actually, greater than or equal to 1, in all cases, f of z naught is equal to 0 for n greater than or equal to 1. And g prime of z naught is not equal to 0, right? Since z naught simple 0. So this thought bubble here, right, justifies this equality right there, okay? Which establishes rule 3 in the case that n is greater than or equal to 1. So what's the next case? What if n is what? So less than or equal to 0? Right? Or then what? We have f of z over g of z equal to what? Oh, I'm an idiot. I'm sorry. Let me not be a dummy. Ay, ay, ay. Sorry, I've lost my way. Let me track back here for a second. Is there another case? Oh, the other possibility, of course, is that f does not have a 0 at z naught, right? Okay. Duh. I don't know what's wrong with me here. Continuing, so either f has a 0 at z naught, or it doesn't. So f of z naught is not, so I'm sorry, so like, you know, this is the case right here, right? So this is to say f of z naught is equal to 0, right? So this observation down here is kind of like, duh. That's what we're assuming at the start of this case-wise argument, right? It's not something I'm deriving, it's something we've assumed. So the fact that this would be 0 should have been immediate from the outset if we were paying better attention than I was. So sorry, guys. Now, if f of z naught is not equal to 0, then what? Then f of z over g of z is equal to f of z over z minus z naught times hg of z, right? As z naught is simple pole, simple 0 rather, for g, right? So here, hg of z is holomorphic at z naught, and hg of z naught is not equal to 0. So if you look at that, what we have is f of z over hg of z divided by z minus z naught, right? Which shows that f of z over g of z has simple pole at z naught. Thus, the residue of f of z over g of z at z naught is equal to the limit as z goes to z naught of z minus z naught times f of z over h sub g of z divided by z minus z naught, which is what? So that gives us f of z naught over hg of z naught. So what's left to prove? Right, we'd like that hg of z naught is g prime of z naught. But that's just a short exercise to show, right? If g of z is equal to z minus z naught times hg of z, then g prime of z is hg of z plus z minus z naught times h prime g of z, right? And so if you, by the product rule, and if you evaluate that at z naught, what do you get? You get g prime of z naught. And so there you go. Rule 3 proved. We used rule 1, of course, to take that limit. So if you can get past my stumblings, there really wasn't much to this proof. Really, we just have to break into two cases and think carefully about the case that f of z naught is 0 versus the case f of z naught is non-zero. In summary, if it's 0, we can either prove it's a removable singularity, or it's just that the quotient just straight up has a 0, which then means that the residue at that point is 0 because residues are only non-zero at a point if the point is singular, right? If the point is singular, it may or may not have a residue which is non-zero, but certainly a residue is going to be 0 at a point if that point is not even a singularity. In the case, which was essentially the case, well, it was the case when n was greater than 1, it was a removable singularity if n is equal to 1, in which case it's not a pole, therefore the residue is 0. On the other hand, the other case, when f is non-zero, we can prove basically by an application of rule 1 and an identification of what the, what's this hg of z mean as it relates to the derivative. Well, it's just the derivative at the point when we work out the calculus there. So that's rule 3. Any questions? So take a step back. What does Cauchy's general integral formula say? What did it say? It said the integral of f of z over z minus z naught to the what? M plus 1 dz over, over appropriate curve. Let's just say appropriate curve C is equal to what? 2 pi I times what? What's that? F what? Well, but this is m plus 1, right? Yeah, so the mth derivative at z naught over what? M factorial, right? So here the picture, I don't know, whatever you want your crazy thing to look like here. I know, it could have a hole, could have a couple holes, 3 holes, whatever. Anyway, somewhere in here is your z naught, right? And this C is the boundary of some bounded region D. That's the context in which the generalized Cauchy integral formula holds, right? But on the other hand, the residue theorem holds, right? What's the residue theorem say? I'm assuming that f of z is holomorphic in D, in the sense that it's holomorphic in and near D, except what? Well, excuse me, there are no exceptions. So if f of z is holomorphic in D, that means that when we look at the integrand here, it's only singular where? At z naught, right? So by the residue theorem, this is also equal to 2 pi I times the residue of what? F of z divided by z minus z naught to the m plus 1 at z naught. And so this gives us a sort of a level M, a rule M, the mth rule, if you will. And here it is, the residue of a holomorphic function. I think I need that, well, maybe I need that f of z. What do you think? Do I need f of z naught is non-zero for this to make sense? What do you guys think? I think I need that f of, I think I need that, I want to say I need f of z naught. It's non-zero for this rule to hold. Well, what do you guys think? Be conservative. Okay. It still might.
Because if f of z is equal to z minus z naught to the f plus 1, does it still hold?
Well, let's just try out something simple. What if we had the integral, say, over the modulus of z equals to 1 of z dz over z squared, right? So here I'm thinking of z naught is equal to 0, and I'm thinking of f of z is equal to z. So clearly f of 0 is equal to 0, which would violate my rule. And my claim is that, okay, so that's, here is m equals to 1, right? So I'm claiming that that's f prime of 0 divided by 1 factorial which is equal to 1. Oh, and I've lost my ever important 2 pi I times the residue. So, well, I mean, well, go back to the Cauchy generalized integral formula. Was there any assumption that that the function had to be that the holomorphic function had to be non-zero at the singular point? No. So this is just me worrying and not unnecessarily. So there you go. That is kind of a, we had rule 1 for simple 0. We had rule 2 for a double 0 in the denominator. This is if you have a m0 in the denominator, if you like, assuming of course then my comment is necessary that, well, m plus 1 to 0, I suppose. Anyway, yet another way to calculate residues. Now that is helpful for which problem? We were looking at this earlier, James. Which one was that we were talking about? The one with the sine over z minus I cubed or something like that? Yeah. There's one with a cube in the denominator, which you might need this rule for. Okay. All right, so moving along here. So, all right, in summary, to calculate residues, you can use these rules, or, of course, you can go back to base principles and just, find Taylor series for everything in sight and form appropriate quotients with long division. Just focus your attention on, isolating the reciprocal powers in the Laurent expansion about the singular point, or you can use the rules. And which is the right way to do depends on the problem, but it should be a relatively straightforward process to calculate the residues for most of these functions we're looking at. So now we turn our attention to look at some applications of the residue theorem towards the calculation of integrals. And so on section 12.2, there's a typo, unfortunately. So here's the basic idea. And so the title is Integrals Involving Rational Functions, well, featuring rational functions. So the big idea here is to look at a half circle, right, or a half disk, I suppose. And so this would be D, right? And so these points, this is R, this is minus R, right? And look at it counterclockwise, and then this one down here is like that, right? So if you look at this curve we're looking at, the boundary of D is like the circle of radius R. Maybe I put a plus on that this semester. I've been putting a plus up there for like the upper half, I don't think in the notes I think I just said CR. You can use whatever notation you think is best, but and then union with minus R to R, right? So that's this piece down here, of course, right? And the thing is, if we want to look at the integral over the boundary of D of f of z dz, what's that going to be? Well, that's 2 pi I times the sum over zj singular inside D, right, of the residue f of z comma zj. So to picture it, maybe this is Z1, this is Z2, this is Z3, etc., right? You've got these isolated singularities of your function, which is, otherwise holomorphic. So we're looking at a function which is meromorphic on D, and all but except a finite number of poles. And then the residue theorem says that the integral around the boundary of D is given by that, right? But on the other hand, we can break the integral around the boundary into two pieces, right? It's got the integral over the upper circle plus what? Plus the integral along the line segment and so let me just give you the big picture. If f of z is equal to like p of z over q of z, with the degree of q of z greater than or equal to the degree of p of z plus 2, plus 1, I guess, is enough, right? 2, yeah, 2. Thank you, 2. Then we can find a bound. Then you can find f of z, right, is less than or equal to something like m over r squared. Well, let's say let me give some names here. Let's say that the degree of q is n, and let's say the degree of p is m. So this is less than or equal to the, m over what? R to the n minus m, right? Where r to the n minus m is, well, more to the point, where n minus m is greater than or equal to 2, right? Which of course means that as r goes to infinity, that goes to 0, but that alone is not enough, right? So if this is the case for, r sufficiently large, we have that the modulus of the integral over the positive part of f of z dz, right, is less than or equal to m divided by r to the n minus m, all right, times what? Times L, right? By the ML theorem, what's the length of this upper half circle? Yeah, just pi r, right? And then the thing is, so you've got, pi m over r to the n minus m plus 1, and that goes to 0 as r goes to infinity. Since n minus m plus 1 is greater than or equal to 1, right? So what's that say? That says, if we look at this, and so, to be honest, perhaps we should adorn the region D with like a little sub r, because we're not really looking at just one region. We're looking at a whole family of them parameterized by r, to be more honest, right? And we're looking at, as we take this half circle and blow it up to the entire upper half plane in some sense, well, something magical happens, right? This integral, right? The integral on the upper half circle that piece of the integral goes to 0, right? So, therefore, the limit as r goes to infinity of the integral over the boundary, over the good grief, yeah, boundary of dr of f of z dz, right? And it's always equal to 2 pi I times the sum of the residues. I mean, once r gets to be sufficiently large, you've encapsulated all of the singularities of the rational function, right? So this doesn't change past some r. And of course, that's reasonable to think about because we're taking the limit as r goes to infinity. But on the flip side of things, that's equal to the limit as r goes to infinity of the integral over CR plus f of z dz plus the limit. And this step I'm making is reasonable because I just proved that the first thing I'm taking the limit of, in fact, vanishes. Integral of minus r to r, f of z dz, right? So, I mean, we've just shown that this is, in fact, going to 0, right? I mean, I showed that the modulus of it goes to 0, but if the modulus of it goes to 0, it goes to 0. And so what's remaining? What are we looking at here? We're looking at the limit as r goes to infinity. And so how do you actually parameterize this line segment? What does minus r to r look like? We have z equals to x, right? For minus r less than or equal to x less than or equal to r. So dz is just dx. So that is just the integral from minus r to r of f of x dx. Which is by definition the principal value of the integral from minus infinity to infinity of f of x dx. Then, if we have separate reasoning that the integral from minus infinity to 0 and the integral from 0 to infinity separately exist, then we can break that principal value up into a sum of integrals from like 0 to infinity or rather minus infinity to 0 or 0 to infinity. But the principal value can exist even when the double integral from minus infinity to infinity, when the integral from minus infinity to infinity existing means that you can pick some point in between minus infinity and infinity, calculate the integral to that point from minus infinity to the point, and then calculate the integral from the point to infinity, and both of those things separately exist. That's what defines the integral from minus infinity to infinity, a la calculus 2. The principal value, you notice, is based on the symmetric limit from minus r to r. So like, if you take an odd function with odd function which has a symmetric domain about the origin, well, suppose an odd function which is defined on the whole reals, the principal value is 0, right? Because the integral of an odd function from minus r to r, integral of an odd function is just straight up 0, right? So principal value of an odd function will exist even when the function doesn't limit to 0 at infinity, because this is just identically 0 for all r. So principal values sometimes exist even when integrals don't exist. That's why it's important for me to say principal value at this point. Yeah. On the other hand, this aspect of it, proving that there's a bound like this, that's that horrible homework problem you guys had before, right? Yeah.
What is the principal value?
Definition right here. I know, right? Yeah. Now, there are actually are applications where principal values have physical meanings and so are interesting in and of themselves. But yeah, that's it. It's just that, yeah. I think there are other meanings for principal value beyond that, which I'm not sure we get to or don't get into here. I can't remember. I think maybe it for this semester.
Really? Class?
Yes, James, for the whole class. You're on your own for Richet's principle and that other stuff. I'm not going to teach it to you. People are going to think I'm talking to myself. Let's see here. Which may or may not be true. I don't know. All right, so let's do an example that's very simple, but you know, it's a useful example. So integral from minus infinity to infinity of dx over 1 plus x squared, right? Or I'll say x squared plus 1, just because I like it more. All right, x squared plus 1. Now, you guys have known how to do this since calculus. Well, it depends on wherever you first covered improper integrals, this would be one of the early examples, right? Inverse tangent, the answer is pi, because you get pi over 2 minus a minus pi over 2, because inverse tangent of a large number is pi over 2, right? But how would we derive this with our current technology? So what we're going to do is we're going to look at the integral over, the boundary of dr of dz over z squared plus 1, right? So that's going to that's going to be the 2 pi I, the residue of, 1 over z squared plus 1 at what? So notice z squared plus 1 is z plus I times z minus I, right? So as we look at the half circle in this case, there's just one residue inside the upper half circle, right? Namely I. So I only need to look at the residue of 1 over z squared plus 1 at I, right? And that's going to be equal to the integral. And so when is, you guys tell me in just a second here, CR plus dz over z squared plus 1 plus the integral from minus r to r of dz over z squared plus 1. So at this point, I usually divide and conquer. I call this part 1, 1. I call this 1, 2. Right? Now, when is this a legitimate equality here? What this is for R what? Here's what R couldn't be. R could not be a half. Right? If R was a half, it'd be like this, right? So the lower, the diameter here is on the x-axis. So in order for the equality that I put at the top of the board to be legitimate, R must be greater than 1, right? Just saying. So then let's look at number 1. Number 1, we'll notice that if the I think it's enough to say if the modulus of I'll find the words eventually here, guys. If R is greater than 1, then you can tell me, what about 1 over z squared plus 1? This is less than or equal to what? Absolute value of the modulus of z squared minus 1, right? Which is, by the way, equal to 1 over r squared minus 1. thus the integral over CR plus of dz over z squared plus 1 modulus is less than or equal to pi r over r squared minus 1. At which point I go, and that goes to 0 as r goes to infinity, right? There's a feather in our cap. It's a little Robin Hood-based comment there for you here. There's a new Robin Hood coming out. You guys see that? It's very exciting. Can't they come up with any new stories? I mean, like, Robin Hood, what's next? Shakespeare? Let's see here. There's got to be some artsy director making a Shakespeare movie like every month of the year. Yeah.
So over there, didn't you assume that that was always going to be 0? Or
This is a general template for the argument, but I'm actually not using it as a theorem at the moment. I'm suggesting that we actually go through those steps for examples. Now, we should agree on some kind of language that keys you into whether or not I want to see these details, right? Something like, you are free to use the theorem about integrals featuring rational functions, which says a certain integral goes to 0 appropriately. Some sentence like that should be explicitly included in the problem if I don't want you to actually go through what I'm doing right now, which is just recreating the magic, which is that horrible homework problem that you did for arbitrary order polynomial earlier, paired with the ML theorem here. However we slice and dice the work, definitely that piece goes to 0 as r goes to infinity. And on the other hand, 2 is the integral from minus r to r. If we calculate the limit as r goes to infinity of this thing, what do we got? Minus r to r of dx over x squared plus 1. Right? In other words, the principal value of the integral from minus infinity to infinity of dx over x squared plus 1. Right. And then, so let's put all the pieces together here. What's left to do is to calculate the residue, right? So point number 3, what's the residue? So what would you guys suggest we use for this z squared plus 1 residue at I? Rule 4, I like rule 4, which says what? 1 over 2z evaluated at z equals to I, rule 4. So that's 1 over 2i. Therefore, connecting the dots, going back to my original, let me call it star. Therefore, star yields that 2 pi I over 2i equals to the principal value of the integral from minus infinity to infinity of dx over x squared plus 1. In other words, it's pi I. Pi, rather. And then if we know that the integral from 0 to infinity exists, right? If we already knew that somehow, then this implies that the integral from minus infinity to infinity of dx over x squared plus 1 is equal to pi. If we also know that that integral exists. So if I'm not interested in the arguments that that integral exists, then I'll just say calculate the principal value. Right? For this class, I'm much more interested in executing 1, 2, and 3 than I am in the arguments which show that that integral exists. Let's look at another example. So you kind of see that we can calculate the integral of just about any rational function where the numerator has degree 2 less than the denominator by just integrating the same function with a z and calculating the sum of the residues in the upper half plane, right? Then that's going to give us the integral of such a rational function. So that's the first example we have of using the residue theorem to do an integral, which maybe we couldn't have done before, right? Well, that's probably not honest. I think we could do these integrals in calculus too. It's just a matter of, do you have the will of fire to go through the partial fractions decomposition for the rational function and then to execute the necessary and proper integrals to actually work it out to the end, right? I mean, it's kind of beastly. Kind of beastly. So here's a picture of the one we just did. Here's another one. I'll fix it for you. Oh, we're good? Oh, okay. Cool. So here's integral of 1 over z to the 4th. Certainly calculating the partial fractions decomposition of this directly you could do, but it's nice that you don't need to. So if you look at this, the singularities are the 4th roots of minus 1, right? And so if I look at what are the 4th roots of minus 1, so that's the 4th root of e to the, what is minus 1? E to the pi I, right? So it's that, and then I times that. Let me call this thing gamma. I gamma minus gamma, and then minus I gamma. There's your 4th roots. The principal 4th root is e to the pi I over 4. So it's basically one of these, one of those, one of these, and one of those. So if you look at that, there's 2 of those. These 2 guys are going to be in a half circle that's sufficiently large, right? So when I apply the residue theorem, that's why I'm looking at e to the pi I over 4 and I e to the pi I over 4. Those are the 2 singularities that matter, that are enclosed in our contour. So Cauchy's residue theorem implies this. It doesn't say this directly, right? But there's what? There's the integral over the CR plus, which is going to 0. And so it just leaves me with that. So here, see here, Bethany, I'm using by proposition 12.21, which is to say that I'm endorsing your program of action, which is not to reinvent the wheel every time. So I'm putting words in your mouth, but they're words you endorse, right? Okay. So just to be safe. What we got here? So you got yourself 2 pi I, and you got these, yeah. So anyway, you do some arithmetic, and you get pi over root 2. So there you go. And it follows that this integral exists because, well, you could compare it to like the integral of x squared dx over x squared plus 1, right? That's a larger integral which exists, is it not? Because 1 over x squared plus 1 is greater than 1 over x to the 4th plus 1 for x sufficiently large. So by comparison, if the integral of 1 over x squared plus 1 exists, then surely this integral exists as well. Just saying. Whoa. Wolfram alpha. Look at this. So here's the straight up Calc 2 integral of this, which then you could evaluate at r and take the limit as r goes to infinity, see what you get. Somehow it works out to pi over root 2. I think I like our residue theorem way of doing it, don't you? So next up, guys, we can do things like p of x over q of x times like a cosine. So maybe I'll start next class with that one. I got to think about it. But here I show that you can do something like integral of e to the a z over z squared plus 1. That's going to pick up a cosine and sine integral. What's much more, so we keep doing, these ones are kind of like, okay, basically we're taking a function that kind of looks like the real function and just doing a complex integral, right? These are pretty direct. It gets weirder. So the next section is based on, check this out. Well, I'm trying to do this next class as well. But you can also do integrals from 0 to 2 pi of trigonometric functions using contour integration. Does this look like a complex integral from minus infinity to infinity? It shouldn't, because it isn't. But what you can view this as is a parameterization of the integral around a unit circle of this function. So I show you how to do that next class, hopefully. And then, of course, to calculate this, you just got to figure out if there's any singularities of these. Use the residue theorem. Bam, you've calculated this integral. So this is a little bit sneakier, right? Once we get past that, then the next page in our playbook is branch points. We learn how to do these sort of keyhole contours to like loop around singularities in a certain way, and so we'll get to that. I'll hopefully start talking about that next class. Definitely I should be to it by Friday. And that's pretty much all she wrote in terms of our others fractional residues. You can, if you got a singularity on the edge, you can like do something like this. So these are the things we're talking about this week. This week is just methods of integration using the residue theorem. So for many complex variables courses, this is essentially the punchline of the course. So once we're past all this, we will do the logarithmic integral and Roche's principle, and that's pretty much it in terms of complex analysis. We then turn to a calculus integration for a couple days, and that's it. So it's been a nice semester.